Thank you for the kind introduction. My name is Avi, working as a research scientist at Google Brain. However, this talk will mostly focus on the work that I did as a graduate student at UC Berkeley. And let's begin by considering a somewhat typical robot reinforcement learning example, wherein we have placed a robot on in a sort of like tabletop manipulation setting in front of some new objects, and the robot slowly begins to explore this environment by performing a random walk. And since this robot doesn't really have any priors, it would explore this environment in this fairly inefficient way, trying out a lot of sort of unproductive things before it encounters any high reward states or actions. This kind of learning is completely different from how a person might learn a new task. Let's say a person is interested in playing tennis. And if they have some prior experience playing a related sport, such as squash, this amount of transfer from a prior skill can be substantial. And even if they haven't played squash, but they know how to move their arms and legs in a directed fashion, that can still serve as a pretty powerful initialization for acquiring this new skill. And so the question that some of the work that I've done in the last 2 years or so has addressed is, what is the best way to utilize prior experiences in the case of robotics for the purpose of learning new tasks as fast as possible? Typically in machine learning, this is formulated as the meta-learning problem. In case of Ariel in particular, an agent is trained in order to optimize its return over a distribution of MDPs in a way such that when given a new MDP, this agent can explore quickly and also exploit sort of like learn a high return policy really quickly. And while this has been shown to be effective in certain simulated domains, doing something like meta-RL for a real-world robotic setting can be quite challenging. You'd essentially have to set up a lot of tasks in parallel at the same time, keep them running, sort of like synchronize into a centralized learning process, and it's going to be a big systems effort to get there. What if we consider a slightly sort of like more reasonable setting? Let's say we have a robot sitting in the robot lab, and over the course of an year or so, this robot acquires a lot of different skills over the course of various robotics deadlines. So it learns to play baseball, learns to play ping pong, and learns to play soccer. And if we're using a data-driven method to acquire these skills, then over the course of acquiring these skills, it would have collected some data for each of these skills. This previously collected data set can be a demonstration data set if we were using an imitation learning technique to acquire the skill, or it could be a reinforcement learning data set, so an offline RL data set if we use reinforcement learning to acquire the skill, and we would also have reward annotations in that case. And now we would sort of like to use this fixed sort of static data set that's sitting on our disk to learn, to sort of like, we would like to leverage this data set to learn a new skill as quickly as possible. In other areas of AI, this kind of transfer is typically achieved through some form of pre-training. So if you're interested in training a new object detector for, let's say, your room, you would probably pre-train this detector on a large-scale task, such as emission classification and object detection. Similarly, if you are trying to train a dialogue agent, you would probably pre-train it on some kind of a next word prediction task on a large text corpus. And while this kind of pre-training is the norm in most other areas of AI, it's not quite as mainstream in it's not quite as mainstream in RL at this moment. And sometimes the requirements for pre-training for RL can be a little different from requirements in other areas. For example, if you are trying to learn, if you're trying to pre-train for computer vision, learning good representations of input agents might be sufficient to achieve good transfer. However, if you are doing this for RL, what you're actually looking for is something more along the lines of input-output relationships. And these input-output relationships can be fairly complex depending on how diverse and varied of a data set you are dealing with. And you might need to capture things like multimodality. There might be many different actions that make sense in any given context, depending on what your intent is. And even for the same intent, there could be many different actions that make sense. And each of these actions will influence future observations. And so in this talk, I'll essentially talk about a few pre-training methods essentially for RL for faster acquisition of new skills. And let's try to formalize this problem setting a little bit. So our training data essentially consists of interaction data sets from a wide variety of tasks. In this case, some kind of object rearrangement tasks involving a lot of different kinds of objects. We would like to extract a prior from all of this data. And now, given a new environment with some new objects, we would like to explore a diverse set of behaviors in this environment. And we would also like to quickly learn an RL policy that maximizes the reward in this new environment. There are two works that I will be talking about in this presentation. The first one is called Parrot, Data-Driven Behavioral Priors for Reinforcement Learning. This was presented at ICRA last year. And the second work, which is not publicly released yet, is called Ariel, Leveraging Prior Datasets to Automate Robotic Reinforcement Learning. And I'll first talk about Parrot, and then I'll talk about Ariel. In Parrot, our solution is to essentially use generative modeling to learn from past experiences. And the assumption that we make here is that most of our prior data is expert or near expert data. So we are in a sort of imitation followed by RL setting, except the data that we have can come from, it's sort of expert data for a wide variety of different tasks instead of expert data just for a single task. And so to model this multitask imitation data, we use generative modeling. This takes inspiration from recent work in generative modeling of text, where you train a large neural network, typically a transformer, given where, and you prompt this transformer. I'm sorry, was there a question? Okay. Where you prompt this transformer, and you also pass some noise to this neural network, and given these two inputs, it's able to generate a new sequence of words. In our setup, we do something similar. Our neural network, given some observation input, outputs an action. And once again, to capture the multitask and multimodal nature of our data, we pass some noise to it, and we use a model parameterization that is capable of dealing with this multimodality. We parameterize the prior in Parrot using flow-based generative models. Flow-based generative models are a class of generative models that can transform samples from a simple distribution, such as standard Gaussian, into samples from arbitrarily complex distribution. They have some nice properties, such as the fact that you can always condition this sampling process on extra information, on context. In our case, this context consists of an image observation from the environment. And we can use flow-based networks to essentially optimize the exact conditional log likelihood of all the actions in our prior data set conditioned on the observation. So in a way, it's performing imitation learning on the entire multitask data set, and it should be sort of capable of reproducing all the many different skills that you saw in this prior data set, given the right context. And importantly, even given the same context, it can perform many different skills. One last property of flow-based models, which will come in useful later, is the fact that flow-based models are invertible. So for any given output or any given sample from this flow-based model, which is an action in our case, there has to exist some input which will lead to that action. It's mathematically guaranteed. Let's now take a look at what sampling trajectories from this kind of a flow-based prior looks like. We see that the agent now directly interacts with the object or objects in the scene and sort of like tries out grasping or pick and place behaviors with them. However, simply having a prior is not enough to solve a new task, because in any kind of realistic environment, there are many semantically meaningful things that you can accomplish. And so the robot needs to have the ability to try out all of these things and then zero down on the one that maximizes its return. And so now we'll see how we can combine such a pre-trained prior with reinforcement learning to do this. Mathematically speaking, the prior is a function f that takes two inputs. The first input is the observation O from the environment, which could be just a camera observation. The second input is a random noise vector, let's call it Z, and it outputs an action A such that when you execute this action in the MDP, you're likely to it's likely to lead to some kind of a high reward behavior. But as I said, now that this MDP is new, so we don't know exactly what kind of high reward behavior did the user intend when they placed us in this new MDP. And this is where reinforcement learning comes in. So we essentially close this loop by introducing an Ariel policy. This Ariel policy also takes the observation O from the environment as input, and it outputs Z, which then gets passed over to the prior F. So in a way, the policy is essentially learning to control the prior in conjunction with the MDP to sort of control the environment or to achieve its goal. And from the standpoint of the Ariel policy, it's essentially just working in a transformed MDP where instead of directly executing actions on the robot, it instead controls what kind of action the prior will execute on the robot. And so this is a sort of a simpler problem for the reinforcement learning agent, because the prior is much more, the prior is sort of biased towards action that are more likely to lead to high reward states based on all the data that it saw in the past interacting with various other objects. And then we can use our favorite reinforcement learning algorithm to update the parameters of this Ariel policy while the prior stays fixed. Another thing to note is that the prior is trained just once across a variety of tasks, and then it can stay fixed for downstream learning. This is also the part where the invertibility property of the prior, which is represented by a flow-based model, comes into play. Since the policy controls the environment via Z instead of A, it is important that it has the ability to still try out new things in the environment and not just the actions that the prior is biased towards. And it is allowed to try out these new things because of this lossless and invertible nature of the prior. Let's now summarize some of the discussion in Parrot through some visualization. So random exploration is quite slow. We can substantially speed up exploration and try out a diverse set of behaviors as well if we use generative modeling to model our prior data. And in Parrot, we essentially present a method to combine one such class of generative models that are flow-based models to combine these methods with Ariel in order to optimize the reward for a specific task of interest in this downstream environment. There's a fair bit of prior work in hierarchical reinforcement learning that our work is closely related to. But there are some significant distinctions as well. Most prior work in hierarchical Ariel typically aims to learn both the downstream, both the low-level policy or options, as well as the high-level policy using reinforcement learning. And so you essentially stay in a single fixed environment and you break down sort of like larger problem, typically temporally extended problem, into smaller problems, and then you learn to combine the various solutions together. Whereas in our work, we're focused a lot where, first of all, we learn the low-level policy using generative modeling and the high-level policy alone using Ariel, which, among other things, also allows us to be pretty efficient in the overall process. There's another class of works which combine hierarchical limitation with reinforcement learning. And this is sort of like more closely related to what we do in this paper. But the difference is that this class of work, once again, is based on learning in a single fixed environment. Whereas in our case, we are really interested in learning new tasks really quickly through making use of these pre-trained priors. And since we are focused on learning new tasks really quickly, the specific choice of how we parameterize the prior, in our case using a flow-based model, was really important because this flow-based model allowed both expressivity and flexibility via the invertibility property when trying to learn this new task. So you can still try out new things and go beyond the prior set of skills that you acquired. We evaluate our method on a suite of robotic manipulation tasks involving some kind of object rearrangement, either picking up objects or picking them up and placing them on some other object or putting them inside a container. All of these tasks are vision-based tasks, so the robot doesn't really get the object positions directly. They need to be inferred from camera images. And the object arrangement is sort of randomized at the start of every episode, so you need to be good at perception to solve these tasks. And further, we use sparse rewards for all of these tasks. So you get a +1 reward only upon the successful execution of the entire task, and a reward of 0 otherwise. These two factors, sparse rewards and image observations, make the overall RL problem somewhat complex. We compare our work against both ablations as well as prior work. Compared to RL from scratch, our method does a lot better because RL from scratch is essentially not really able to solve these tasks, mostly due to the sparse reward nature of the task. As compared to prior works in hierarchical learning of skills followed by downstream RL, our method still performs favorably. These prior methods also do okay on these tasks, and we see that on a number of tasks, they're able to obtain a success rate that's respectable. But they're not quite, they typically flatten out more quickly, whereas our method is able to sort of like keep learning and achieve higher overall success rate, which we attribute to the more flexibility that we get from having a more representative generative model, and also a generative model that allows the policy to have complete control over the final action executed in the environment because of its lossless nature. Parrot does quite well compared to prior methods. There are still some limitations which make it difficult for us to sort of take these results to the real world. And so now I'll be discussing or sort of giving like more of a preview of this upcoming work where we try and overcome these limitations and present results on actual hardware as opposed to just simulation. First of all, the prior dataset needs to be an expert or at least a near expert dataset for best downstream performance. This is not strictly a requirement, but in practice, this is what works best when you are following more of an imitation plus RL approach. And the second drawback is that downstream RL can still be pretty expensive. We are still talking about thousands or sometimes tens of thousands of episodes in order to learn the new task involving new objects and whatnot. This can be quite problematic in the real world, since in the real world, we sometimes need to provide additional supervision to the robot in the form of, let's say, performing resets for the robot and ensuring that everything is running as intended. And in the more recent work, we essentially target these two issues. We remove our dependence on having expert or near expert prior data sets, and we also ease the downstream learning process through drastically reducing the number of manual resets needed for real-world policy learning. This work is called Ariel, Autonomous Robotic Reinforcement Learning, and the autonomous part essentially is implying to the fact that we are trying to reduce human interventions as much as possible when trying to learn a new downstream task. Stage 1 in Ariel is done using offline reinforcement learning. So we are once again provided with a large multitask data set of a robot interacting with objects in the real world. But this time, these data sets are not necessarily expert data sets. They could just be the robot attempting various tasks. Occasionally it succeeds and occasionally it fails, which has all been labeled through some kind of reward function. We take all of this offline prior data and we train a multitask offline RL policy. We use an off-the-shelf offline RL reinforcement learning method. And in order to make this policy work for many different tasks, we essentially learn a context variable for each of these tasks. And given this multitask policy, we would now like to use it to speed up learning of a new task. And we would like to learn this new task in a way such that it minimizes the number of resets that a human operator has to perform. And so to do so, we don't really learn one new task, but we learn two tasks, wherein the first task, which is learned by the policy that we call the forward controller, is our task of interest. And the second task is essentially a reset controller for the first task. So the job of the second task is to reset whatever was achieved by the first task. If the first task was, let's say, putting a spoon on a plate, then the second controller would essentially be interested in taking a spoon outside of the plate and placing it elsewhere in the scene. And so we can then alternate between these forward and backward controllers to autonomously practice a task without any human intervention or with very infrequent human intervention. The forward controller essentially explores the environment in order to collect the data that is needed to learn the skill well, and the backward controller resets the environment. We now take this entire data set, our entire offline prior data set, and the online data that we collect for 2 new tasks, and we use all of this data to essentially update our forward and backward controllers, which share the same multitask backend, but have different context variables, which are also learned from the data. I'll now show some results. The one set of tasks that we tackle are these kind of pick and place tasks. So where the goal is to pick up an object and place it inside some container. The training and test objects for this task are shown on the right. So the upper half of the image is training objects, and the 4 objects in the bottom row are test objects. Most of the data collection process itself is autonomous because we use scripted policies. These scripted policies don't exactly work very well. Their success rate can be as low as 30% for certain objects. But since we use offline reinforcement learning, we are essentially relying on the Ariel algorithm to distinguish between the good and bad trajectories and learn from them. Here is what the downstream learning process looks like for a new task. The goal here is to place the toy elephant inside the bowl. And we see that the robot is trying out both putting the elephant inside the bowl, and every once in a while, when it does succeed at that task, it then attempts to put the elephant back outside the bowl. And we're not able to do this yet fully autonomously, so we do require a human intervention every 20 and 30 minutes. I'm not sure if you saw a human hand sneak in once. But this is a lot less frequent as compared to what would have been required with the sort of standard online RL, where you need an intervention more like every minute or so. This is what the final learn policy looks like. So we see that the agent is able to accomplish the goal for many different initial configurations of the object in the environment. We also test all of these out in tasks involving manipulating a drawer. So the goal here is to open a drawer and then place an object inside it. And once again, this is what the learning process looks like, where the robot is trying out opening the drawer, picking up the object, and then it also tries out closing the drawer. So that it can try out the whole thing over and over again. And once again, we have autonomous resets for the most part, and human resets every 30 minutes or so. This is what the final learn policy for the drawer task looks like. Another benefit that we get from using this kind of multitask pre-training approach is that our policy generalizes better if you just put in entirely unseen objects in front of it. Because the neural network backend was trained on a variety of different tasks, it learned more useful visual representations. And so if you just like give it completely new objects, you see that the success rate is much higher as compared to a policy that was trained just on the downstream task. So you get this like extra bit of robustness and generalization through this multitask pre-training approach. We also perform a lot of simulated experiments in this work, and where we compare against not having prior data and other prior works that do reset-free learning. And we see that we're able to compare favorably against these methods. In conclusion, Ariel essentially presents a way for you to leverage all kinds of robotic data sets, expert or not expert, and use them to learn a powerful behavioral prior that speeds up learning for a new task. And not only does it speed up learning for a new task, it also allows the robot to learn a reset policy in parallel to the main policy. And so it not only does it allow efficient learning, but it also allows mostly autonomous learning. There are a few future directions that I'm excited about. First one is that we noticed that when we use these kind of behavioral priors, the way that the robot sort of explores the environment is a lot more meaningful and reasonable. It's not, spending time banging against the table and so on, which leads to fear, hardware problems, and so on. So sort of like formally investigating how this kind of sort of utilization of a data-driven behavioral prior can lead to safer exploration for Ariel is an interesting thing to look into. And then I'm really interested in extending these methods and systems to sort of truly lifelong learning setting. In the current setup, we were in more of a two-stage process. So you have a large prior data set from many different tasks, and then you try to learn some new tasks. But in an ideal setting, will we be starting from scratch or nearly scratch? No, we'll be acquiring tasks one at a time, which is a bit more representative of how things happen on hardware. And the goal would be to essentially show that as you keep acquiring more and more tasks, on average, the time that it takes to learn a new task goes down until it goes down to an extremely low level. Thank you to all my collaborators, and I'll take questions.
Thank you, Avi. We have time for one or two questions. Question, I know you have one.
Yeah, I go on. Thank you, Avi, for a really great talk. Really exciting to see how you are using priors to facilitate reinforcement learning. So I had one question with your first presentation on Parrot. Mm-hmm. What if there was a significant data distribution of like what you trained? Because essentially you're constraining your whole action space with Parrot. So what if a new task, maybe this new task required the robot to lift up a block much higher than it ever lifted a block in the original data distribution? How do you deal with that? Or is that a problem with the system?
Yeah, so in short, yes, that is a problem. So we do conduct some experiments in the paper where we were sort of like curious that, okay, like how much can we like deviate from the original tasks that you learned? Yeah. So, we sort of like took all the tasks in our paper and we divided them into like two sort of broad categories. So one is like grasping task, like just pick it up and hold it. And the other is like pick and place. So you hold it and you like drop it somewhere else. And what we did was that we trained the prior on just the grasping task. And then we like we tried to learn some downstream pick and place tasks. And we also did the opposite. We pre-trained the prior on pick and place tasks, and we tried to fine tune on just the grasping tasks. And what we saw was that if you pre-train on pick and place, then you can fine tune on grasping all fine. So it can like successfully ignore certain things that were present in the prior data set. But when you pre-train on grasping alone and you try to fine tune on pick and place, that did not quite work. So it was not able to sort of like acquire completely new skills when, these new skills involve like making like a sequence of decisions which deviate from everything that you have seen in the past.
Yeah. So even though you have this bidirectional mapping, you still have some suppression of useful behaviors.
Exactly. Yeah. So even though in theory, you can always come up with some like input noise Z that will execute the action that you really want, the probability of executing something out of distribution has been pushed down, which I guess gives us faster exploration in the first place.
Yeah.
But then, yeah, this is problematic when you're trying out something really new, and that something new requires you to sort of like, take like 10 actions in a row that deviate from whatever you've seen in the past.
Thank you.
All right, let's thank Avi again for this talk.
Thank you.